All right, welcome back. This is where we left off. Sign magnitude notation, largest and smallest values. So where we're going from here is we've talked about how numbers are represented on a computer. All right, we know that they're going to be in binary. We've talked about sign magnitude notation. Now the question is, how do we represent other things on a computer? So let's start with text. So storing text on a computer. Now, it all still ties back to binary. All right, so basically what we do is we assign every character a number. So we're still storing text as numbers, but it's then the program that interprets those numbers as letters or words, when we're actually displaying them to the screen. So text is stored as a series of characters. Each character is represented by its own unique pattern of zeros and ones, which is essentially a number. And then computers use ASCII code to represent characters. 1 byte is used, which means you have 8 bits. So all those different combinations that are possible give you the different letters and characters that you might need. Now, if you haven't heard of ASCII before, maybe you've heard of Unicode. Just know that ASCII is a subset of Unicode. All right, and basically what it breaks down to is when you're only using 8 bits, that's actually not enough space to capture all of the different characters that are out there. All right, in English, yeah, this will probably get it done. But once you start moving over to other languages, there's a lot more characters, there's a lot more symbols, there's accent marks, there's things like that. So ASCII actually doesn't provide enough opportunity to store or represent all those characters. Remember, it's only, if we've got 8 bits, all right, we have 2 to the 8 unique combinations that we can represent, right? And that's not enough when we start looking at worldwide languages. So Unicode uses more bits so that it can store more characters, and ASCII is like a subset of that. So in Unicode, you could think of this would still be like lowercase a, only there'd be a bunch of zeros in front because you're using more bits, and those zeros give you more options because if you start flipping them, you can start getting characters in other languages and other things like that. So just realize that words, text, letters are stored as numbers. Those numbers correspond to whatever letter or character you're talking about. And the system that organizes that is called ASCII, which is a subset of Unicode. And there's actually another little video that I've attached to this assignment that you can watch that just goes into that in a little more detail. But the main idea is we're still storing numbers, which is why we're spending so much time on binary and all those other things. It's just that those numbers are basically codes or represent specific letters that we want according to some predetermined setup. And that predetermined setup is ASCII or Unicode. One is just a subset. ASCII is just a subset of the other. But that's basically, it's the table or the lookup table that kind of corresponds the number to whatever character you're talking about here. All right, so storing text on a computer. So let's say we wanted to show the ASCII representation of the characters what. All right, so we would go to our table here, and we would say to ourselves, okay, uppercase W is 0, 1, 0, 1, 0, 1, 1, 1. All right, and I'm just going to kind of block this off so that our ones and zeros don't start running together. That would be our uppercase W. If I wanted to know what lowercase h was, I would go over here, and I would get 0, 1, 1, 0, 1, 0, 0, 0. That's my lowercase h. And then I would just keep going. All right. I would just look up one letter after another. All right. I would encourage you to do that. I'm just going to put them down here, but, just look them up. It's kind of like, it's almost like decoding a secret message or something. So 011000001. That's our A. 01110100. That's our T. And then our question mark is 001111111. All right, that would be our question mark. All right, so basically this is just a giant lookup table. You go and find what you're looking for, like, where's the question mark? Oh, there's the question mark. There's the uppercase W. There's the lowercase h. There's the lowercase a. There's the lowercase t. And then you just copy the code down. And you can do the same thing in reverse. So this says, what do the following ASCII characters spell? So you would just go look for this pattern. All right, they go in order here in this table. So 0, 1, 0, 0, 1, 0, 0, 0, 0. That's right here. All right, so that would be our uppercase H. Then we've got 0, 1, 1, 0, 1, 0, 0, 1. That is right here. That would be our lowercase I. So far, let me put that right underneath it. So right there, we've said hi so far. All right, this one, 0, 0, 1, and then a whole bunch of zeros. We can actually see that that is the space. All right, that's the space. So even if you hit the space bar, that's represented by a sequence of 1s and 0s so that the computer knows, like, okay, it's a blank space. It's a character. You might not think of it that way, but when you hit the space bar, you're inserting the space character. Then we've got 0, 1, 0, 0, 1, 1, 0, 1. All right, which is the uppercase M. All right, so we've got that. Then we've got 0, 1, 1, 0, 1, 1, 1, 1, 1. Let's see, that would be the lowercase o. Now, this one and this one are exactly the same thing. All right, so we know that this is an uppercase M. And then this last one here, 0, 0, 1, and then 0, 0, 0, 1, 1 is right after the space. This would be our exclamation point. All right, so just realize that even when we're talking about something like text, it's still breaking down to binary numbers, 1s and 0s, stored on the machine. And then just one thing I want to note is that in ASCII, upper and lowercase letters are always 32 apart. All right, so if we look back at this table, lowercase a is 97. Uppercase A is 65. That's 32 apart. B is 66. B is 98, 32 apart. So the question is, why 32? Well, 32 is a power of 2. So to convert between upper and lowercase, all you have to do is flip a single bit. So it makes it very easy for computers to go between the uppercase and the lowercase representation of a letter, because all you have to do, so you only have to flip one bit. So if we think about the letter uppercase M, all right, so we'll go back to that mom example. All right, here's the letter uppercase M. All right, now remember, this is your 1 spot, this is your 2 spot, this is your 4 spot, This is the 8 spot. This is the 16 spot. This is the 32 spot. This is the 64 spot. This is the 128 spot. So to flip that from upper to lowercase, they're always 32 apart. So all you have to do is turn on that 32 bit, which is currently off, and you're going to get the lowercase version of the letter M, and that works for any letter. All right, so that was done, obviously purposefully, to make it really easy for computers to go between upper and lower cases. They made them 32 apart so that you would just have to flip a single bit. That's, it's this kind of thing that just, it's interesting. Like, you start to learn more about computers and you see how thought out and how clever everything actually is that's going on inside. So we figured out that we could represent text with numbers. And then when we set it up, we was like, all right, let's be smart about this and make it very easy to kind of go back and forth between upper and lower cases. So that's what they did. And all you have to do is flip that single bit back or forth, and you can go from upper to lower or lower to upper just by switching that one bit and setting it to 0 for the uppercase and setting it to 1 for the lowercase. So anyways, I think that's kind of neat. But let's continue. So we're storing text. We're storing 8-bit numbers. As soon as we started storing text, the next thing that people started thinking about is like, how can we save space? All right, so we've got this text. How can we save space so that we don't have to use 8 bits for every single letter? Because if we did that, text would start to take up a lot of space pretty quickly. All right, so we're going to kind of work through these, and we'll take a look at a couple of different ways that this problem has been approached. So the simplest would just be keyword encoding. All right, this is just where you say, all right, I've got certain words that I know pop up a lot. So instead of storing that entire word, let me just store a symbol that corresponds to that word. All right, so here I've got the sentence, the systems must not only work independently, they must interact and cooperate as well. And then I could set up a table and say, all right, well, anywhere where I see the word must, I'm going to replace that with an and sign. And anywhere that I see, so there's another one right there. And then anywhere where I see the word and, I'm going to replace that with a plus sign. So there's my plus sign. And then if I have the word those, I'll replace that. If I have the word that, I'll replace that. If I have the word well, there's the word well. Let me replace that. But basically, you're replacing entire words with symbols. So instead of having to store all 4 of these letters as separate characters, I can store one character and save on space. All right. Again, same thing. Instead of 4 separate letters, 1 character. Here, it's only 3 letters that I'm trading out for 1 character. But this same idea. All right. Now, when we're compressing things, we usually want to know, like, is it worth it? All right. Because if we do something like text compression, we have to then take time later on to uncompress it. All right. So, like, it might be a good way to, like, send a file because it can cut down on the size. But if it takes too long to uncompress it so that it can actually be displayed to the screen, because if we're displaying it to the screen, we don't want to display the system's and sign. We want to display the system's must. So we have to spend time and energy going back and forth. So we want to make sure that it's worth it. So usually what we do is we calculate a compression ratio to see exactly how much space we're saving. So to calculate an compression ratio, you start with the uncompressed size. So uncompressed. Now, in this example, you would count up all of the characters. All right. Now, when you count up the characters, you've got 1, 2, 3. Don't forget the spaces, 4, so on and so forth. Don't forget the space here. But assuming I didn't screw up, and I counted it a couple of times, so I'm hoping I didn't screw up, there are 87 characters in total in that sentence. Now, we've already said that we're encoding using ASCII, ASCII uses 8 bits. So if there's 87 characters and each of those characters take 8 bits to represent, that tells me that I am using 696 bits. Now, once I compress it, that number is going to go down. Because instead of using 4 different characters here, I've reduced it to 1. So I saved 3 characters here. I saved 3 characters here. So that's 6 characters I've saved so far. I saved 3 characters here. So that's 9 characters I've saved so far. And then here I only saved 2 characters because it was a shorter word. So that's 11 characters I've saved so far. So if I've saved 11 characters, that means I went from 87 characters to 76 characters. They still require 8 bits for a total of 608 bits. So the compression ratio is just putting the compressed size over the uncompressed size. So when we're doing a compression ratio, all right, it's just the compressed size over the uncompressed size. Now, it should go without saying that if we're doing compressed over uncompressed, this number should always be smaller than this number, which means your ratio should always be less than 1. And the smaller it is, the greater compression you're getting. All right, the larger it is, you're not getting as much bang for your buck. If it's 1, that means your compressed size and your uncompressed size are the same, so you didn't actually compress it at all. But in this little example here, it would be 608 over 696, which is roughly about 6/7. So it's about 6/7 of the size, or if we're going to be more exact, 0.8736. So you could think of that as like 87.36% of the original size. Now, this is probably just the most basic. This isn't something that's going to get used a whole lot because by the nature, if I use these symbols, I have to make sure that those symbols are nowhere actually in the document. So it can work for like a little example like this, but what if there was like a plus sign somewhere else in my document? All right, my computer might all of a sudden think that's the word and then it gets screwed up. So keyword encoding, it's good. It illustrates the purpose. I mean, it illustrates kind of the idea of compression, but it's not something that we're really going to spend a lot of time talking about because it's not something that's going to get used, all that frequently. One that we are going to spend a lot of time talking about is called Huffman Encoding. All right. And if you've ever zipped a file or unzipped a file, you have dealt with Huffman encoding. And the intuition behind Huffman encoding is that characters like A and space appear all the time. All right, it's pretty hard to write a sentence without using the letter A or having a space. In fact, it's probably impossible to write a sentence without having a space. So we should use fewer bits to represent things like A and space than we should a character like X, which rarely appears. So a Huffman code uses variable length bit encodings to represent characters. And what that means is instead of everything being 8 bits, the more common characters are shorter and the more uncommon characters can be really long. So, frequently used characters get short encodings. Rarely used characters get longer encodings. Okay. So, for example, A might get the Huffman code 00, where then E gets 01, L is 100, O is 110, R is 111, B 1010, and D 1011. And what you'll notice about this is that the way that they start, it's impossible, and the codes are generated in a very specific way, so that there can never be ambiguity about what code you're dealing with. So no other letter starts with 00. No other letter starts with 01, so that you're always confident that you're using the right letter. These are generated in a very specific way using something called the binary tree to make sure that you don't ever accidentally create a sequence that could be mistaken for a different letter. All right, so let's take a look at an example here. So using Huffman codes, doorbell in binary would be, all right, so the D is one of the less common letters, so that would be 011. There's our D. O is 110. Then we have another O, so that's 110 again. Then we have an R, whoops, put it in the wrong order there. Our R is 111. Our B, that's one of our less common ones, so that's 1010. Our E is one of our super common ones, so that's just 01. And then we have two L's, so those are both 100, 100 for two L's there. All right, so again, the encoding works the same way as it would with a full ASCII table. Instead, we just do it we do it this way so that you're saving space, all right? We're not using 8 bits every single time. Some of them have different lengths so that we don't run into those problems. And then if we compute the compression ratio on this, all right, the original word was 1, 2, 3, 4, 5, 6, 7, 8. All right, so that means 8 characters times 8 bits is going to be 64 bits. But again, we'll go through it one step at a time. So it's compressed over uncompressed. All right. The uncompressed size was 8 characters times 8 bits, so 64 bits. And again, that's coming from the 8 characters times 8 bits per character. And then the compressed version would be 25 bits, I believe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 22, 25. Yes, 25 bits. So by using this Huffman encoding table, we actually get a ratio of 0.39, which you can also think of as 39%. So we've reduced the size of the encoding by 39%. Now, when it comes to Huffman encoding, there's either sort of a standard Huffman encoding that can be used for smaller files, or if it's a really large file, you can create a custom Huffman encoding table. Right? For some things that are really small, it might not be worth the time and energy to create that table, because if you think about it, if you're trying to compress the file to send it over the internet, if you use a non-standard table, you have to send the table. Otherwise, the other side, the person that receives it's not going to be able to decode the message. So if it's too small, it's not worth it, because the space that you saved by compressing it, you're going to lose by having to send the table along with it. In contrast, if it's a really big file, it might be worth it to customize your Huffman encoding table, because the space that you're going to waste sending the table is going to be more than made up for by having a custom Huffman encoding table versus just like a standard English language Huffman encoding table or something like that. So what I have right here is this would be a Huffman encoding table for the Lord of the Rings book. All right, so we can see that with this table, E is the most common letter in the Lord of the Rings. It shows up 91,054 times. So it's only using 3 digits for its Huffman code. All right, so there's 3 digits that it's using for its Huffman code, versus the Z only shows up 283 times, and that uses 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it uses 10 bits, which is actually longer than a standard ASCII encoding. So some of the less frequent things can actually end up being less efficient, but you more than make up for that because you're using E 91,000 times and you're only using 3 bits now instead of all 8 bits. So Huffman encoding gets used a lot. All right, it gets used when you're compressing documents. It actually also gets used when you're compressing pictures and things like that. You can take advantage of repetitions in the colors and things like that. And movies, same deal, because movies are just consecutive pictures shown one after another. So Huffman encoding gets used a lot in compression to make files manageable sizes. Without it, movies and pictures would be gigantic. This kind of allows us to sort of condense them down using a similar premise, just that things that appear more common should get shorter codes, things that appear less common should get longer codes, and then the time spent having to convert back and forth is worth it because you're saving so much space in the long run there. So again, a useful tool and something that's used pretty frequently in computer science to save space and go through that. Now, we just took the word doorbell and converted it to binary. Let's say that I wrote, let's see, what word can I make out of this? There's not a lot of choices here. Let's say I wrote out this. 1 0 0 1 1 0 1 1 1 0 1. All right. If you were going to decode this, if you were going to go in the other direction, you basically start and you say, all right, 1. All right, where are all the ones that start with a 1? Okay. And then you go to the 0 and say, all right, there's the 1 zeros. And then once you get to this and you see that this is a complete code, you know that that's a letter, all right? Because those prefixes are unique. So once you see a 100, you know that it has to be an L. There's not going to be anything else in your table that starts with 100, right? The prefix or the start of these are always unique. So as soon as you match one, you know that you're on to the next letter. You don't have to keep going at that point. As soon as you make a complete match, you can stop. So on this one, I've got 1 1, okay? So I'm either looking at this or this, and then it's followed by a 0. I can stop at this point. I don't have to look down here and see if there's any other 110s that are longer. The prefix is always going to be unique, so I know that this has to be the O. Again, the same thing. I go 1 1. All right, I'm here, but then the next one's a 1. All right, it has to be the R. There's no other option. And then 01 has to be the E, so this would be the word lore. All right, so again, the way these tables are set up, once you find the match, you know you're good. You don't have to go any further. And that's kind of the genius of how Huffman codes work and how they're set up. All right. So again, just another way to sort of compress and save data so that we don't have to use the full 8 bits for every single one that we're dealing with. All right. So one last encoding one that we're going to talk about is called run length encoding. Okay, so run length encoding is used in situations where you're likely to have like long sequences of the same character, something like DNA, all right? DNA is obviously a very long sequence. So when we're trying to store it on a computer, it's helpful to be able to condense it down. All right, so here's how run length encoding works. You start with a key, all right? And the key is how you kind of alert the system that like we're about to do a encoding. All right, so this is our key. After the key, you put the character that you're going to be repeating. So in our case, it would be a T. This is our character. And that's followed by the number of times that that character repeats. So if I've got a 5 here, this is saying that there's 5 repetitions of the letter T. Right? Now, we don't do this for everything. With C, we would just write C. There's no special code because we're not repeating everything. With something like G, here, that encoding would be star G2. You'll notice that would take 3 characters versus just writing out the G and the G. So we just write out the G and the G. All right. The idea is to save space. This would actually waste space and time and energy because eventually we'd have to decode it. So GG we would just repeat there because compressing would take more characters. So let me just write that there. Compressing would require more characters. All right. Then we've got A. All right. So this one we're definitely going to compress. All right. So we've got an asterisk. We've got an A. And then, assuming I didn't count incorrectly, we've got a 12. Now, anytime there's more than 9 repetitions, it's a little confusing, but right here, even though this is a 12, as humans, we write 2 digits. All right, so when we're talking about like how much space did we save, if we look at this, we're like, oh, well, this is still 2 characters. Yes, as a human, it's 2 characters, but a computer can store this as a single 8-bit number. All right, so as part of the encoding, it knows that when one of these sequences is initiated, this last part is not actually going to be stored as like a ASCII code. It's going to be stored as an 8-bit number. So even though we're writing 12 here, when we calculate the compression size, we're not going to be treating this as 2 characters. We're going to be treating it as a single 8-bit number. And then from there, the T is by itself, so that's there. And then with the G, we're going to go star G4. And then I want to just make a special note about this. 4 is the smallest size that makes sense to encode. Right? And the reason it's the smallest size that makes sense to encode, with 3 repetitions, you don't save any space because it's going to require 3 characters to represent the encoding. But you waste time encoding and decoding. All right, so unless the sequence is 4 or longer, there's no point in actually encoding it because with 3, you'd spend 3 characters to encode it anyway, so you're not actually saving any space. So, long story short, this is what's called run length encoding. If you wanted to do the compression ratio, which why wouldn't you? Just remember that it's compressed over uncompressed. So the compressed is now 1, 2, 3, 4, 5, 6, 7, 8. Even though this is 2 digits, we're only counting it as 1, 9, 10, 11, 12, 13. So it's 13 characters, or 13 times 8 bits, over the full length size, which, assuming I didn't count incorrectly, was the 25 characters times the 8 bits, because they're all ASCII. Now, effectively, the 8 bits are just canceling out here, so it's 13 over 25, which gives you 0.52 or 52%. So you've basically cut the size down almost in half using this run length encoding. So those are some of the ones that you want to be aware of for this course: run length encoding, keyword encoding, Huffman encoding. You know, are there other encoding schemes out there? Yeah, I'm sure there are. But these are the 3 that you are kind of responsible for in this course. You should know how to both take a string and run length encode it, or if I give you a run length encoding, you should be able to produce the original string. Same thing with Huffman codes. You should be able to go back and forth in either direction using as long as the table is provided. All right. So that kind of wraps up what we're going to talk about regarding text. All right. So we've seen that text can be stored as numbers, and we just have to know which numbers correspond to which letters. Right? What we're going to move on to now is pictures, because actually most of the programs that you write in this course are going to deal with like pictures and sounds. So let's talk about how pictures are represented, and more specifically, how color is represented on a computer. So representing color on a computer. So we're going to put this in terms of painters, and then we're going to put this in terms of computer screen. So in art class, if you're talking about the primary colors, I did not know this, but apparently the true primary colors are magenta. Who knew? Cyan, again, who knew? And yellow, that one seems to make a little more sense. All right. Now, paint is what's called subtractive. All right, which means that the paint absorbs light to produce the color. All right, so the different color paints are absorbing different amounts of light or different wavelengths of light. In contrast, computer screens and the human eye are additive, which means they add lights of different wavelengths to produce color. In this scheme, the primary colors are R, G, and B for red, green, and blue. All right, and again, these are additive, where we're adding lights of different colors, of different wavelengths, sorry. To make colors. So if you combine red wavelength light with green wavelength light, you're going to get a different color than if you combine green wavelength light with blue red light, wavelength light, and so on and so forth. And this RGB for red, green, blue, the human eye has these color receptors. All right, so again, we've got this intersection here of kind of like computer science and biology. Which is what we kind of talked about at the very beginning when I said like analog versus digital. You know, we try to simulate the analog world and digital, and how good of a simulation we need to do is kind of dependent on like our biology and our human limits and stuff like that. So again, there's this neat intersection. So the way it works is on a computer, we store certain levels of red, green, and blue. And when those levels are combined, they produce colors. So if we store 0 red, 0 green, and 0 blue, that produces the color black, because it basically means we gave you no red light, we gave you no green light, we gave you no blue light. So that's going to produce the color black. Now, if we want the color white, all right, that's actually having full red, and we'll talk about why it's 255 in a second, full green, and full blue. And then you can start making other colors by altering these values. So you could get a yellow by doing 255, 255, and 0. All right. You could get a purple by doing a 192, a 0, and a 192. And it doesn't have to exactly be 192. Variations on this are still going to look very purpley. But all of these are going from 0 to 255, which, if you think back to binary, implies that each one is using 8 bits. So when we store a color, what we're actually doing is we're storing 3 numbers, right? And each of those numbers is being stored using 8 bits. So we get a number that basically indicates the amount of red, the amount of green, the amount of blue. We get a number that indicates the amount of red, the amount of green, the amount of blue. Each of those numbers require 8 bits to represent, because they can go from 0 to 255. And then it's up to the program and the computer and the processor to interpret those numbers correctly. Just like when we're dealing with text, all right? It's up for the computer and the processor to interpret those numbers as text, but they're still just storing numbers. Same thing with the picture here, all right? We're still just storing numbers, but it's the program that knows to interpret those numbers as colors when it's displaying a picture or when it's showing a movie or something along those lines. Also, when you're doing colors, it would be really annoying to write out binary, because if each of these is 8 bits, you'd have to be writing out 24 ones and zeros, and it would be really easy to make a mistake. So a lot of times when you're dealing with colors, you're actually going to see the hexadecimal representation of the color. So if you remember, 4 binary digits is 1 hexadecimal digit. So if you've got 0, 0, 0, remember, each one of those is using 8 bits, so that would correspond to 6 hexadecimal digits. So in hexadecimal, we might write this as 0, 0, 0, 0, 0, 0 to show that it is using 24 bits and they're all 0. For white, we would write F, 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 F to again show that it's 24 bits in total. And this right here would be your red. This right here would be your green. This right here would be your blue. All right. Yellow would be F, 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 0, 0. Again, your red, your green, your blue. And then, assuming I didn't goof this up, purple would be C0, 0, 0, C0 for, again, your red, your green, and your blue. So a lot of times when you're seeing colors represented, you're either going to see them represented like this, hexadecimal, or you're going to see them represented with their decimal equivalents. Usually we don't write out 24 ones and zeros, but that's what's actually being stored on the computer, is that string of 24 ones and zeros. All right, so this is how color is represented. How do we represent an actual full picture? Well, a picture, if I can find the sheet here, is just lots of individual colors. So what happens is the digital image is divided into pixels, all right? And you can basically think of pixels as the individual points of light on the screen. So you can basically think of this as being divided up into a giant grid, all right? And obviously the grid is actually way more, these boxes would be way more small on the computer, but the idea is sort of the same. Each of these boxes represents an individual pixel, and then we can record what are the color values at that individual pixel. You know, if this is water, maybe the red is 0, the green is 0, and the blue is 255. All right, right here where the wave is cresting, you know, maybe that's white. So maybe here the red is 255, the green is 255, and the blue is 255. So the picture is broken down into individual little pieces. We store the color information on each of those individual pieces as the amount of red, the amount of green, the amount of blue. Now, a picture is made up of a lot of pixels, and again, that's where the compression comes in, right? Instead of having to store the exact full 24 bits for every single pixel, we start to find ways that we can condense it down so that we get that same information without having to store each one independently. But basically, to kind of summarize what's happening here, it stores the average color found in each pixel as 3 numbers. And those 3 numbers represent the amount of red, green, and blue. All right? And again, they scale from 0 to 255. But when we're storing an image, again, it's just a whole bunch of numbers, but it knows to interpret those numbers as colors. All right? Which brings us to the final slide of the data representation, which is sound. All right? So that's the other thing that we're going to be writing programs involving. We're going to be writing programs involving pictures. We're going to be writing programs involving sound. So how is sound stored? All right, so sound is stored as a sequence of numbers. Again, it all goes back to numbers. Recording the height, or if we're going to get fancy, amplitude of the sound wave at regular intervals. All right, so let's imagine you had a sound wave. There's my sound wave, all right? It's the vibrations in the air. To represent this, we've set a fixed interval all right? And the smaller our interval, the better we'll be able to reproduce the sound. But like, all right, there's interval 0, 1, 2, 3, 4, 5. And then what we do is we just record the height at that interval, all right? And we just keep recording the height of the wave at that interval. And what that's going to do is it's going to allow the computer to reproduce the sound wave, all right? When you are running a program that knows to play a sound, it's going to take those numbers, it's going to feed that into the program. That program is going to communicate with your speakers, and it's going to produce the appropriate sound wave based on the numbers that are recorded, all right? But all you're doing is just sampling from this wave at fixed intervals, all right, seeing what the height of the sound wave is at those intervals, all right? And that's what you're using to recreate the wave. All right, that's the digital representation of an analog sound wave. We just keep taking points from it, recording those amplitudes, and then storing them on the computer. All right, so the one big idea, all right, the big idea that you should be taking from all of these things that we've been talking is everything can be represented as ones and zeros. And maybe I shouldn't have written everything. I mean, can love be represented as ones and zeros? Can the entirety of human compassion and emotion be represented? Anyways, you get the point. What changes is how we interpret those ones and zeros. All right? Are we interpreting them as color? Are we interpreting them as sound? Are we interpreting them as text? Are we interpreting them as numbers? It's up for the computer and the programs to figure out how they're being interpreted, but it all comes back to ones and zeros. Everything on your computer, everything that you're storing, everything that it's dealing with is dealing with ones and zeros. All right, so this marks the end of the data representation. What we're going to do now is we'll head into some actual programming stuff, and that's going to be kind of how this course goes. We'll talk about some aspect of a computer, then we'll do a little bit of programming. Then we'll go back to the computer, then we'll do a little bit of programming. Then we'll go back to the computer, and we bounce back and forth kind of all year long. But this is the first sort of computer section, and then we'll move into programming next week. So again, hope this was useful. As always, let me know if you have any questions or if I forget to post it like I did last time, and then we'll go from there. All right, thanks, and have a good day.